All right. So the Hoffman rearrangement involves this weird disconnection between the R group of an amide and the carbonyl carbon, and it's like you extrude CO2 and you get the corresponding amine out of this. Now there's lots of different ways to make amines, and I'm not claiming that this is a particularly good one. But it's instructive in the sense that it also involves migration of an R group to an adjacent electron deficient atom that has a leaving group on it. So you need base because the first step is you remove a proton. Fine. I never like it when textbooks say proton transfer and don't show you, but on the other hand, they're so easy to draw that maybe we don't need it, I don't know. All right, so you remove the proton from this primary amide. This only works for actually primary amides. You need to not have any R groups on this nitrogen. And you can draw the following resonance structure where the negative charge is on the carbonyl carbon. At this stage, you've got bromine as an electrophile, and so oh wow, that's just horrific, isn't it? Terrible. So the negatively charged nitrogen attacks bromine, and you form a new nitrogen bromine bond. And again, heteroatom bonds are generally weak, and so the nitrogen bromine bond is definitely weak, and bromine's a good leaving group. So the pattern you've got here is an R group that's adjacent to this electron deficient heteroatom that has a leaving group on it. And it turns out the rearrangement can't happen on its own at this stage. You have to first remove the proton. I think that makes the carbonyl carbon a little bit more electron rich such that the R group can migrate. So again, we remove a proton from the amide nitrogen. And now we're in a situation where the carbonyl carbon is electron rich such that if this group moves over, migrates, it's now, as we've drawn it, it would be lined up with the NBr sigma star, moves over, and if at the same time we kick electrons down from the oxygen to the carbonyl carbon, what we have at that point is a strange intermediate called, what is that? Is that an isocyanate or something? We're gonna have to find out. That's another thing. If you can name exotic functional groups without looking them up, people think you're cool. Yes, that is an oh, Wikipedia wants me to pay. Not gonna do it. Right, so you get this weird isocyanate, and what can happen now is under basic conditions, you can add oxygen to the carbonyl carbon. Oops. And you can then protonate the resulting intermediate on the nitrogen. And that converts your isocyanate into this functional group, which is carbamic acid. Now, you've seen something probably in your experience with OChem, you've seen something like carbamic acid before in protecting groups. Have you ever seen a protecting group like this? You have, I know you have, but you probably haven't thought of it because Bach, right? Or this could be something else, FMOC, right? But do you remember the mechanism for deprotection for like Bach? Yep. You need acid, T-butyl leaves. You generate a carbamic acid, and then how do you free the amine? Anybody remember? I'll give you a clue. Look at the products.
Don't you just deprotonate the acid and then protonate the amine?
Yes, right. It's a decarboxylation, right? If you were to remove this proton, and if you remove that proton, then you have the resulting carboxylate can kick off the amine as a leaving group. So that's just for your reference. So we'll just delete that. So what likely happens at this stage? Yeah, you've got base catalyzed decarboxylation. Notice the difference between FMOC and Bach deprotection is only in what generates the carboxylate. What follows after that is exactly the same. So we'll use a base to remove a proton from the carbamic acid. And electrons kick down, and as the amine is leaving, it picks up a proton, because we don't like negatively charged nitrogens as leaving groups generally. And so what that then gives us is CO2 and our amine, and then we'll regenerate our base. Okay, so the key step, I mean, the players are different. The unique thing about the Hoffman rearrangement relative to things that we've done earlier is that we're losing CO2, but the basic rearrangement step is this one. And the pattern is you've got an R on an electron-rich carbon adjacent to an atom that is electron poor, potentially has a leaving group on it. All right. You want to say about that? They get somewhat worse. Yeah, lovely, huh? All right, so the next rearrangement we'll talk about is the Schmidt rearrangement. I have to be careful saying that one. And this takes a ketone and HN3, which is a fairly weak acid, and it's going to convert them to an amide. So what we're basically going to do is break one of these bonds, insert a nitrogen in there, and it looks like we're going to lose nitrogen. Azides as a functional group are useful for a lot of different things, but one of their most useful properties is that you can lose N2 from them, and so you can use them to do unusual types of things. It may be useful to remind yourself what the various resonance structures of azide are. So you have this one, it's a negatively charged ion. You can, if you want, draw resonance structures where you make a triple bond here and have two negative charges out on that nitrogen. If we put a proton there, then this would be HN3. Okay, so our first step is going to be to protonate the carbonyl oxygen with the acid. Boring that step. Once we have the protonated ketone, we're going to have azide act as a nucleophile, and we're going to add to the carbonyl compound to get this intermediate. And for now, I'm not going to draw the azide, the actual Lewis structure of the azide. But this looks something like a hemiacetal intermediate or something that you get on the way to imine formation. We'll then use another equivalent of acid to convert the OH into a good leaving group. And now I will draw the resonance structure of azide. We can draw it like this. Or, if we wanted to, we could draw it like this. You see how we got from here to here? We just move those electrons over. Okay. And from this resonance structure, you can see you've got basically nitrogen gas embedded in that functional group. And that's an excellent leaving group. So maybe you're starting to see where we could be going. What we're going to do is use the electrons on the negatively charged nitrogen of our azide to kick down and get rid of water as a leaving group. And that's going to give us this really strange intermediate. It kind of looks like a hydrazide or hydrazone. Kind of looks like a hydrazone, only you've got nitrogen here instead of an NH group. It sort of also looks like an imine. All right, but look at the situation that you've got here. Again, you have an atom that has a good leaving group on it. We'll use green for the good leaving group. And then you have an R group adjacent that's going to do the migration step. So in that migration step, R moves over and nitrogen leaves. Now, there are two R groups here. Presumably the one that is anti to the nitrogen is the one that leaves. People have done studies in terms of which groups prefer to leave and which groups don't. But for useful sort of purposes, we're going to imagine doing this on molecules where the R groups are the same, because I think it's difficult to control which ones migrate. In the studies that have been done, usually it's the largest, but in any case, after that happens, we have an intermediate that looks like this. Let's see. No, I think we want, oh, brother. this is a resonance stabilized intermediate, we can actually draw it like this. And this looks kind of like an intermediate we've seen before in these migration reactions. But to get to the amide products that you see that we're supposed to get, all you have to do now is have water attack the carbonyl carbon. And at this stage, I'm going to skip over a few proton transfers. Let's show you. All right. Hopefully you can recognize this as the enol sort of tautomer of, and I think it's called imidate. But all you have to do at this point is to tautomerize, and that gives you your amide. And by tautomerization, I mean we need to protonate this nitrogen and remove a proton from that oxygen, and we're done. All right. So the key step, the key rearrangement step, is very similar to what we've seen previously. An R group moves over to an adjacent atom that bears either a leaving group or has a positive charge on it. Yeah.
What used to introduce the azide ammonia?
Sorry, what? How do you
introduce the azide to attack? Is it ammonia?
What induces the azide to attack here?
Yeah.
Yeah, the fact that the ketone is positively charged now.
Yeah, can you use this? Can you react to the ammonia or just have azide N3 to react?
Could you just use
NH3?
NH3 to do what? Rather than the azide.
Yeah.
No, because you need
N2.
the N2 as the leaving group. Yeah. If you use ammonia or any other amine, you can make an imine, but the nitrogen, which is sort of what we've done here, but the nitrogen of the imine would not have an N2 attached to it, and so you can't do the rearrangement. Okay. So we're continuing on with sort of weird name rearrangements. I want you to have seen them once, and I want you to see that the key step in all of these is a migration of a group to an adjacent atom that has a leaving group on it. This is called Baeyer-Villiger oxidation, and it's a nice way to do a ring expansion to convert a ketone into a lactone. Yeah.
The previous reaction. HN3.
Yes.
Is that what introduces azide?
That's right. HN3 is azide. So we could draw HN3 is just this. Yeah. All right. So as an example, in the Baeyer-Villiger oxidation, you start with the ketone and you need some kind of per acid. This is a peroxy acid. You've got the oxygen-oxygen bond. We use these to make epoxides as an example. But what this will do is it's going to, looks like it inserts an oxygen into the six-membered ring to give you the ester rather than the ketone. So this is sort of like Lego type chemistry. Pop the two groups off, insert oxygen. But the mechanism for that is a is a step similar to the ones that we've seen. So maybe what we'll do, instead of pushing all the arrows, I'll talk you through to the key intermediate. So we protonate the oxygen using this per acid, and then the negatively charged conjugate base of the per acid attacks the carbonyl carbon, and we get an intermediate that looks like this. Oops. All right, so here is the electron deficient atom. Here is the leaving group. And then you've got an R group here on an adjacent atom that's ready to do the migration. And so what happens is this carbon moves over to make a bond with the oxygen. We have the leaving group leave, and at the same time, if we want, we can kick electrons down from the from this OH group to stabilize the building positive charge that's going to happen as this R group leaves. So if we do that, that gives us our ester, now 7-membered ring with the carboxylate group, and then we can lose a proton to give us the lactone. The evidence for this kind of migration is if you put an O18 label in your starting material on the ketone, that label is still at the carbonyl carbon in the lactone, which supports this sort of migration type mechanism. All right, why would you want to do that? Well, not sure, but lactones are good as often if you want to build larger structures. A lactone is a decent way to do an acylation reaction with some nucleophile to attack the carbonyl carbon, and then the oxygen leaves. It's sort of an upgrade in functional group from ketone to ester. All right. Anything else on that? We're going more and more exotic in terms of the rearrangements, and I'm doing this because it was in your textbook and because I remember vaguely having done it in 552 when I took it 20 years ago. And I think you'll likely hear some of these things occasionally, and I want you to have at least been exposed to them. So the Favorsky reaction or rearrangement is a ring contraction reaction. So it's sort of opposite of the Baeyer-Villiger oxidation. You start out with a cyclic alpha bromo ketone, and then you need first basic conditions, basic aqueous conditions, and then in the second step you need to add acid, and what this does is it contracts the ring and it converts the ketone into a carboxylic acid. And the mechanism here is kind of cute, I suppose. So first, it's thought that you remove a proton from the alpha carbon. Enolate formation using OH minus as a base is uphill in energy, so there's other things that could be happening here. And we could draw another resonance structure for the enolate in which we put a double bond here and a negative charge on the carbonyl oxygen, though it's easier to do the Favorsky rearrangement if you just start with the enolate with the electrons on the alpha carbon. You do a trans what the heck was I doing there? Is that a bond or what? You do a sort of transannular intramolecular substitution reaction to kick off the leaving group. And that's going to generate this sort of weird looking intermediate that looks like it ought to be pretty strained, and it is. You've got a bicyclic ring system with a 3-membered ring fused to a 5-membered ring. All right, and we could look and actually see if that's even possible, shall we? I mean, that looks highly strained. Yeah.
Does the reason that I do it since it's so strained is because you have such a good nucleophile with your negatively charged carbon, and then when you have your bromine leaving group?
Yeah, it's an intramolecular reaction, which means it should be fast. And basically what you're doing in this step is just an intramolecular enolate alkylation. And I'm not claiming that it's that this is a very stable species. In fact, I'm not sure you can isolate that. Whoa, I don't know what I just did. I didn't want to do that. How do I? Ah. Okay. I'm not claiming that's a species you isolate. In fact, the strain here probably is what drives you forward from this point on. So we're going to relieve some of that strain by getting that, making it so that carbon doesn't have to be sp2 hybridized. We're going to attack the carbonyl, and we're going to get to this. Oh. Yeah.
Why is the OH not attacking the carbonyl carbon?
Why is it not attacking the carbonyl carbon up here?
Yeah.
That seems reasonable, and I suspect that's happening, but this is likely an equilibrium process that the ring contraction step is irreversible, and so that's the pathway we go down, even though you can envision attacking the carbonyl oxygen. I think I have to back up briefly because I think it's even weirder than I said. There's evidence that actually before the enolate attacks, the bromine just leaves. And the idea is that and it may be easier to see why it can leave if we draw the resonance structure that shows the enolate in place, right? I'm sorry, shows the carbon-oxygen double bond with a negative charge on oxygen. The reason this is important is because it starts to look like you've kind of got an allyl bromide leaving group. We've seen leaving groups that are adjacent to pi bonds leave before in sort of SN1 type reactions. So it's thought that that leaving group leaves and gets us to this intermediate. And they call this an oxyallyl species. You could, if you wanted, delocalize by resonance this positive charge on that carbon. And you could also, not at the same time, but by resonance, delocalize this negative charge onto that carbon. And the whole thing's neutral, so it sort of works out. But this, it sort of works out as an intermediate, but this is the one from which we close to form the 3-membered ring species that I showed you earlier. So I'm sorry about that mistake. I clearly don't know this reaction very well. That will get us to our strange-looking intermediate. Looks sort of like a kid with a Christmas hat on or something. I don't know. All right, and it's then we're going to get ring contraction once we attack the carbonyl carbon to get our tetrahedral intermediate. Oh, yikes. And this is going to be the migration step. Now, how this happens is unclear to me because the leaving group doesn't seem to be necessarily a great leaving group. We'll have electrons kick down from that negatively charged oxygen, and we'll break this bond and put a negative charge on the adjacent carbon. Notice this intermediate is symmetrical, so if we went the other way, it would be fine. And that generates our now 5-membered ring with an oxygen here. I'm sorry, with our carboxylic acid here. And I wonder whether this group has the potential to leave because it can be protonated as it leaves. This would be a 1, 2, 3, 4, 5-membered ring transition state for that anion to pick up a proton from the acid. And so that would generate your carboxylate, which after acidic workup would give you your ring contracted carboxylic acid. All right, and again, the reason I don't like this very much is that proton's not alpha to a carbonyl, so just your regular sp3 hybridized carbon-hydrogen bond has a pKa of around 40. So I don't love that as an intermediate. I haven't done the calculations for it, but my guess is that that gets protonated pretty close to the time it leaves. We could build a model to see whether that was possible or not. But okay. And the pseudo Favorsky, I don't think I care about enough to have you worry about it. All right, so that concludes our rearrangements. There are some other types of rearrangements that we didn't get to in the chapter on electrocyclic chemistry. Have you guys heard of the COPE or the Claisen rearrangements? COPE has an O in it, but the molecule doesn't have an O in it. That's how you remember. So there are things called 3,3 sigmatropic rearrangements. Sigmatropic rearrangements are rearrangements that involve moving sigma bonds around, but it involves orbital symmetry in terms of what's allowed and what's not allowed. So this is an example of the COPE rearrangement, and it doesn't look like it matters, except for the fact that you can break this sigma bond and make new pi bonds. So you're like, what on earth? Why would I do that? Presumably this involves an intermediate in which you have or presumably this involves a transition state in which you basically have two allyl pi systems interacting with each other, sort of bottom side to top side, and going from this one where these two are a sigma bond to this one where now these two are a sigma bond probably involves this kind of intermediate, or rather probably involves those kinds of orbital considerations. I'll show you one place you may have seen a sigmatropic rearrangement like this. The Claisen rearrangement is an exact analog of the COPE, only you replace one of these corner atoms with an oxygen. And the driving force for this one is a little bit clearer because you get to make a ketone instead of an enol ether. carbon-oxygen double pi bonds are stronger than carbon-carbon pi bonds. So there's a thermodynamic driving force to go that direction. There's also something called the oxycope, but I think that involves having the oxycope involves starting with something like this and then doing the 3-3 rearrangement. And here your product is an enol, which tautomerizes rapidly to the more stable ketone. And so that's another way you can provide a driving force for this rearrangement to occur. These kinds of rearrangements are important, can be important biologically. So don't have this in my notes right away, so we'll just look it up. Have you ever heard of the shikimate in tyrosine synthesis? Maybe in biochem? No, vaguely? All right, don't teach that anymore. Okay, so this is in the synthesis of tyrosine. You've got to make an aromatic ring with an OH group on it. And there's the amino acid tyrosine. Oh, look, we're turning it from an alpha keto acid into an amino acid using some transaminase. And likely the thing that's bringing, it uses glutamic acid and probably to make the amine, and the pathway is going to be somewhat similar to that pyridoxal phosphate pathway that I showed you for amino transfer reactions in biology. But before we get here, nature isn't going to start with the aromatic ring because nature generally doesn't have the electrophiles to do electrophilic aromatic substitution. And so it's got to be more creative and get the functional groups in the right place so that you can introduce first one double bond into the ring, then another, and then in the last step you can oxidize using NAD+ to make the molecule aromatic. All right, so this molecule here is called charismate, and the pattern for a 3-3 sigmatropic rearrangement is a 1, 2, 3, 4, 5, 6, a 1,5 diene. All right, so maybe if I can, oops, sure, we'll just copy. All right, so I'll try to redraw this and maybe help you see a little bit more clearly what's going on. Oops, oxygen. All right, so just like we saw before for the Claisen rearrangement, you have an oxygen-carbon bond, and then on either side of that oxygen-carbon bond, you have these double bonds, right? So we've got that same sort of pattern, and remember the driving force is going to be to convert this enol ether into an aldehyde or a ketone. And so here's the 3-3 rearrangement. and we'll draw the product that forms from that. I think I probably missed some stuff. Now, during the course of this rearrangement, maybe it would help to name these carbons 1, 2, and 3. And then we'll name this 1, 2, and 3. So we're going to break the bond between orange 3 and purple 3, make a new bond between orange 1 and purple 1. What do you suppose the stereochemistry at this carbon is going to be? Quick, move away the answer. Let's imagine a transition state for this molecule where we are rearranging, breaking this bond, making this bond, breaking this one. Making this one. Oops. Breaking this one and making this one. Okay, it's going to attack from above or below. Well, it was above on this side. Now, this gives us a chance to talk about orbital symmetry issues. Imagine these two groups being sort of side to side. And let's imagine we're we're in a transition state, and so what we sort of have are two allyl systems interacting with each other. You could think of it being allyl radical on this side and allyl radical on that side. But you could imagine that the transition state involves overlap of orbitals like this, and if this were allyl radical, do you guys remember learning that the HOMO for allyl radical, or the singly occupied highest orbital is going to have this C2 type symmetry where the phase changes, right? So I'll draw those orbitals, and in order notice that in order for us to overlap favorably to make a bond here, we have to be attacking the same face of the molecule. In other words, if this allyl system were to come and try to attack from beneath, it would have the wrong phase relationship. The wave function signs wouldn't be the same. There's a whole, and we haven't talked about this in enough detail to have it make sense, but there's a whole class of reactions called electrocyclic reactions that involve orbital symmetry considerations. And the idea here is that you can't break this bond and make this new bond in a single transition state and have purple one attack orange one from below. It has to be from above. And that's what we call a suprafacial rearrangement. That means it happens above or from the same face. Right, so then your stereochemistry in the product is going to be this one. The carboxylate group will be down, and then you have your alpha keto acid here. And I'll just number the carbons again so you can see where everything is. 1, 2, 3, and then purple 1, 2, and 3. And why is this important? Well, it isn't, other than it's a way to show you a sigmatropic rearrangement in nature. However, this pathway, called the shikimate pathway, is the one that is inhibited by Roundup. So Roundup is a product that you use to kill weeds, It will also kill grass in your yard, so you use it to you don't use it on the lawn, and it inhibits this process, and that prevents the plant from making tyrosine, which kills the plant. We don't have this pathway in us, which is why getting Roundup on your fingers does not cause your finger to shrivel up and die. In fact, I believe tyrosine is one of the essential amino acids that we have to get from our diet. Though there is some controversy in terms of Roundup. You've probably heard class action lawsuits because there's allegations that Roundup causes leukemia if you have a lot of exposure. So anyway, but that doesn't have anything to do with the sigmatropic rearrangement. Okay, well, there's more we could talk about. I could tell you about why we get sunburns. Could tell you about why you need sunlight to make vitamin D. But all of that, I think we'll have to wait for some other time. So you've done it. You've survived 552, or rather, you've survived the lecture portion of 552. And now it's time to take the exam. So I'll be around. If you have any questions, please come ask me. I will post the exam and the problem set today. I'll post the problem set key. You don't have to do the problem set. I do recommend looking at it and if you have time, probably trying it. Okay.
Thanks, Dr. Price.
Yeah, you bet.